Have you ever stopped and wondered what really makes a blockchain secure? I mean, it's not a company, it's not some physical vault. It's pure, cold, hard math. And today, we're going to break down that mathematical fortress, piece by piece, and see how it all works.
This quote from our source material just nails it. We're not talking about a company's promise or some fancy firewall. We're talking about mathematical principles that are, by their very design, built to be unbreakable. It's a whole different level of security.
So that's the big question, isn't it? How on earth can a bunch of numbers and algorithms create something so incredibly tough? Well, it all kicks off with a really clever idea, what I like to call the digital fingerprint.
Right, so the very first pillar of our fortress, the foundation of everything, is a concept called cryptographic hashing. The easiest way to think about it is like creating a unique, one-of-a-kind fingerprint for any piece of digital information you can imagine.
So here's the deal. You can take literally any data, a single word, your favorite song, even the entire internet, and you feed it into a hashing algorithm. Bitcoin, for example, uses one called SHA-256, and what it spits out is always a string of characters that's the exact same length. But here's the magic part. It's a one-way street. You just can't turn that hash back into the original data. It's practically impossible.
Now check this out, because this is where it gets really cool. Look at how sensitive this process is. We took the phrase, hello world, and then we changed just one single letter. And the result, a totally different, completely unrecognizable hash. This is called the avalanche effect, and it's absolutely crucial for security.
So for a hash to actually be secure, it needs to have these four mathematical properties. Think of them as the four walls of our fortress. Pre-image resistance means, like we said, you can't work backward. Determinism means it's reliable. You'll always get the same hash from the same input. Collision resistance means it's basically impossible for two different things to have the same fingerprint. And that avalanche effect, it means even the tiniest change is screamingly obvious. Altogether, these guarantee the integrity of the data.
Okay, so hashing protects the data itself. But how do we prove who owns what without a bank or a government stepping in? Well, that brings us to the second pillar of our fortress, the digital signature.
It all comes down to a special pair of keys. First, you've got a private key. This is a massive, secret number that you and only you should ever know. You use it to sign off on transactions, proving it's you. Then there's the public key. This one is mathematically linked to your private key, and you can share it with anyone. It's like your account number, and it lets people verify that your signature is legit, all without ever seeing your secret key.
And this is where you really see the revolutionary power of blockchain. This simple mathematical relationship between your two keys is what gives you absolute authority over your stuff. It cuts out the middleman. No more banks, no more notaries. Your private key is proof. You are your own bank.
All right, so we've got secure data, and we've got secure ownership. Now, how do we link it all together to create a history that nobody can change? Well, you build a chain.
Every single block of transactions has something called a header. Think of it like a cover page with all the important summary info. It's got a bunch of technical stuff in it, but the one we really care about right now, the one that makes the whole thing work, is this one right here, the previous block hash. This is the digital fingerprint of the block that came just before it.
And that right there is the chain in blockchain. It's that simple. Each new block literally contains the fingerprint of the one before it, creating this long, cryptographically linked chain of history. It's like a set of digital dominoes all lined up.
So what happens if someone tries to be sneaky and change a transaction in an old block, like block 101 here? Well, remember that avalanche effect? The hash of block 101 would completely change, and that means the previous block hash that's stored in block 102 is now wrong. It doesn't match. The chain instantly breaks, and that makes the history of the blockchain pretty much tamper-proof.
Okay, but wait a second. In a system with no boss, no one in charge, how does everybody agree on which chain is the real one? This is where the genius of the system really shines. You solve it by making it incredibly expensive to lie.
This is where something called proof of work comes into play. It's basically a massive global competition. Miners all over the world are using huge amounts of computer power to try and solve a really hard math puzzle. The first one to find the solution gets to add the next block to the chain, and they get a reward for their effort.
Now, here's why that's so brilliant. Proof of work ties the digital security of the chain to a real-world resource, energy, and computing power.
So to go back and change that one block we talked about earlier, an attacker wouldn't just have to solve one puzzle. They'd have to redo all the work for that block and for every single block that came after it, all while doing it faster than the entire rest of the network combined.
Which brings us to this big, important number. What would it actually take for an attacker to pull that off? Well, they need to control a majority of the entire network's computing power, what's known as a 51% attack. But for a huge blockchain like Bitcoin, getting your hands on that much equipment and paying for that much electricity would cost billions upon billions of dollars. It's just not worth it. It's what the source material calls economically irrational. So all these foundational security principles were pioneered by Bitcoin, right? But the story didn't stop there. The ideas evolved, and they started to open up brand new possibilities. And you can really see this evolution when you compare Bitcoin and Ethereum. Bitcoin's goal was simple and powerful: secure digital value. It uses a model kind of like digital cash. Ethereum, on the other hand, was built for something different: programmable logic. Its model is more like a bank account, and its code is what's called Turing complete, which is a fancy way of saying it can run pretty much any kind of program you can think of. The simplest way to put it is this: Bitcoin was built to be a digital Fort Knox, an impenetrable fortress for value. Ethereum was built to be a decentralized world computer that anyone can use and build on. They have different goals, but they're both built on that same incredible foundation of mathematical security.
At the end of the day, that's the real revolution here. That's the big takeaway. Through all these layers, hashing, digital signatures, consensus, blockchain gives us a totally new way to build trust. It's not based on some big institution anymore. It's based on math that anyone, anywhere in the world can check and verify for themselves. Which leaves us with this final, fascinating question to think about. Now that we have a blueprint for building trust directly into our technology, right into the code itself, the possibilities are just mind-boggling. What we build with it next is really up to all of us.